Okay, I'm Dan Olds, and I'm here with Jim Fonseca. Jim, am I pronouncing your name right?
It's close. Fonseca.
Is it okay
Depends
if
on
is it okay if we go with Fonseca, or would you prefer Fonseca?
Fonseca. Otherwise, I'll hear that. Uh, I guess throughout the conference.
Good point.
Although depending on where you're from, it can be pronounced differently.
Good. Well, I'm glad we got that out of the way. So what we're going to talk about today is NEMO 5, and more specifically, how it's going to be used in the student cluster competition at SC13 in Denver, and along the way give some of the student teams some hints and tips and possibly alert them to some traps that they might run into in making this code literally scream on their systems during the competition. And Jim, you're a big part of a team that's working on NEMO 5 and have helped develop it, right?
Yeah. So I'm a research scientist in Gerhard Klimek's group, and we're part of NCN, which is Network for Computational Nanotechnology at Purdue University.
Go Boilermakers.
Yep. And so we've got a pretty big group. There's actually three research faculty. We have a postdoc, and then quite a few graduate students, and they're all working with the NEMO code, in different regards, either running simulations or contributing to it. The NEMO is started with Gerhard Klimek's PhD work several centuries ago.
He's well preserved.
So in fact, I think I've got a slide about that to give some of the history in the future.
Oh, excellent. Well, let's jump into this. Next slide, where I guess we're talking about what does NEMO do and why is it useful?
Yeah, so I mean, as you know, the semiconductor industry has been um, trying to make chips faster, smaller, more efficient for several decades now.
Mm-hmm.
And the biggest advantage that NEMO 5 has is that the code is atomistic. So
Hmm.
when you're running the simulation, we are treating every atom. Most tools, and in fact, the industry still uses, take a continuum approach where you have some region and you say, okay, this region is full of this material.
So you're sort of
Um,
averaging it out.
right. And the problem is once you get to, you can see this image of the Intel's the
Tri-gate
22,
transistor,
right,
yeah.
the tri-gate transistors. When you start to get on this scale, atomic fluctuations become more and more important.
Well, individual atoms become more and more important because atoms are sort of lumpy at this scale.
Sure.
And this tri-gate transistor was a pretty big advance in the industry. I remember seeing the initial briefing on it. Um, Being able to come to this exact shape has reduced power needed by this transistor to flip it from one state to another and increase performance at the same time. It's a big
Right.
deal.
Yeah, it is, and I think it's going to continue um, in that same path.
So NEMO then essentially looks at the behavior of materials atom by atom
Correct.
as a
Um,
really stupid,
so
overly broad way to describe it.
I'm sure, and besides say fluctuations, for manufacturing processes, this allows us to look at things. Well, I guess a lot of it is for manufacturing processes, but if you look at some of the items listed here, so you have alloys. Um,
Hmm.
so if you're mixing two different elements together, you're not going to have a perfect distribution of those elements. Then you look at things like surface and interface roughness, where you can probably even see it in this picture. You realize that those lines are not straight.
No. Let's take a look on the next slide. I guess drilling down a little bit deeper.
So in the last slide we saw the kind of the typical state of the art um, industry transistor. But the other side of NEMO 5, besides the industrial side, is the research side. So, researchers are looking at, Intel's interested and, and other companies are interested in what they're going to be doing, 5 years from now. But people are also interested in what's coming, the decade beyond that. So with NEMO5, we're able to look at sort of more futuristic devices like you see here, this transistor, it's comprised of a single atom there.
Wow.
On the right, topological insulators, which are a kind of new type of, I wouldn't say new material, but a material that has interest now because the current flows on the outside. The outside of, if you have a wire, the current is only flowing on the outside of the wire. You don't have current flowing on the inside of the wire. And so you don't get scattering. So the electrons have very good, it's very easy for the electrons to move on the outside of the wire.
I'm still thinking about the implications of the single atom transistor. That's a big deal.
We would like to be able to simulate, things like the picture we saw of the tri-gates, to not just simulate, say, a single nanowire, but I know in collaboration with some groups from Australia, where they've been able to fabricate the device and then simulate it with the software from our group.
Incredible stuff. Wow. So moving along, we have the different evolutions of NEMO.
Sure. I guess just to focus on NEMO5, the idea here is to sort of bring together.
But wow, look at how this is scaled from the number of atoms it can handle.
Well, sure. We want to be able to. We would like to be able to simulate, things like the picture we saw of the tri-gates. To not just simulate, say, a single nanowire, but to, scale up from there.
Wow, that's incredible. What, and I'm seeing here at the bottom, it can be parallelized up to 100,000 cores.
Yeah, we get pretty good scaling to that. We actually have sort of a new push to scale to even scale even more than that. And I think I've got a slide later on about the types of parallelization that we use.
So if someone were to bring 100,000 cores, it would work.
Yes, yep. I've run those before.
So slide 5, atomistic representation of devices.
Sure. Yeah, I think I think we kind of talked about this a little bit earlier, but like I said, that one of the key aspects of NEMO5 is that you can set up any kind of structure that you want. So it's very flexible in that regard. Generally people are looking at silicon, gallium arsenide. The bismuth telluride wire here is an example of a topological insulator. People are interested in graphene. So really, this is what we have in the software now, and but people can add. If there's a new crystal structure, we're doing work on nitrides, so we can add in more materials, if we need to.
This is a hell of a program. And hitting slide 6, what do we mean by a valence force field?
Valence force field is it's actually, if listeners are familiar with molecular dynamics, you've kind of got a similar approach there. It basically describes how atoms interact based on their bonding. So in this case, we have a quantum dot. So I think this is 50 million atoms altogether. I think the dot in the middle is 10 million atoms. So the idea here is that when you have that dot is made of a different material than the large block. And so the electrical properties of this whole system are going to change when all the atoms are sort of in their relaxed position. So when these devices are fabricated, you essentially have to find, what's the minimum energy configuration, or what configuration gives the minimum energy for this structure.
So transport in non-planar structures?
Yeah, so I should say that the last slide And
Oh,
this
sorry.
current slide, well, the quantum dot slide and this slide probably comprise the two, or they are the two types of simulations we deal with most. The quantum dot, you're sort of looking at, okay, what are the energy levels in this particular system? In this current slide, slide 7, we're looking more at, what is the transport through a device? So what kind of electrical characteristics will this transistor give you if you could fabricate it?
And as student cluster competition folks, they don't know exactly what sort of problem they're going to face.
They're going to be similar to those two problems, but I mean, there's a whole plethora of different types of simulations you can run, whether it's the structure of the device or the materials in the device, um, different types of, I mean, here we see the top right figure shows the current voltage characteristic. So how does the current in the device behave as you apply different gate voltage? Um, there are a lot of different kind of subsets of these problems that we can look at.
Excellent. And I think we start to get to the actual program itself on slide 8, right?
Yeah, unfortunately, this is a little dated, but it kind of gives an overview um, of how the software's infrastructure. I don't know how much detail we want to go into here, but obviously you're reading in some input file and a
Mm-hmm.
materials database of what that material is that you want to simulate.
Mm-hmm.
Um, you build up a geometry of that device. So I've got a particular atom located here and another particular atom located somewhere else. Depending on the simulation that you want to run, you're going to set up, different solvers. And without getting into too much detail, there's
Sure.
some information in the NEMO5 manual that can give a better idea of what those solvers could be. For instance, like Schrodinger or Poisson solvers. Um,
And I would assume that you'd advise the teams to be somewhat familiar with that manual and have it close at hand.
yeah, we've been trying to do a lot of work on it recently. But it's probably the first place to look. I don't know if you're going to find all the answers there, but we've been doing a lot of work on it, and I hope that it's useful.
Well, maybe we ought to jump ahead to the next
Sure,
slide.
sure.
Device calculations are typically very time consuming. Well, no kidding. Especially when
Oh,
we're talking about an atom at a time. Because if
sure,
I remember right, I think I'm deep enough technically to say that most devices have a lot of atoms.
sure. And you can see that these things don't really scale very nicely. Um, and so that kind of, necessitates, trying to run on larger computers and optimizing the code as much as we can. Um, you can see here I should have typed it out. The hierarchical parallelization scheme we have is the V is for the voltage parallelization. So if you want to look at how the device behaves, like we had that current voltage curve a couple slides ago. K-space, which is kind of reciprocal space. If listeners are interested in that, if you look into sort of any introductory semiconductor physics textbook, you can find all about that. Energy parallelization, and then spatial parallelization. Similar to what you'd have in molecular dynamics, where you say, okay, I've got this part of the device is all located in one, uh, physical physical region. So we're going to put all those atoms on, one core. Essentially
Gotcha.
just like the picture here is where you kind of split it up.
But it is trying to localize by core common calculations or not?
Correct.
Oh, it is. Okay. Let me ask a high level 30,000 foot question. Is this the type of computation that where it pulls a lot of or a chunk of data into memory and then just cranks on it many different ways? Or is it using a lot of I/O, pulling something in, cranking on it, getting a solution, then pulling in another chunk?
Most of this stuff is going to be heavy on the cranking side.
So highly
Um,
compute intensive.
yes.
And I would imagine memory intensive too then.
Um, yes, it can be. But, but yeah, as far as I don't expect I/O is going to be a big problem, especially at the scale of the clusters for the competition.
But when you say
But you never know.
but when you say it can be highly memory intensive, is that dependent on the data set that they receive? That some data sets will be more, and some requirements, because you're going to lay out a data set and a requirement for them to turn in. Is that Does that data set and the requirements that they're going to have, could that dictate a different memory per core ratio than they might have in a different case?
Yeah, you're absolutely right. And that's probably going to depend just on the details of that particular simulation. Um,
And so a student team that has taken the time and run a few problems with different characteristics might have an idea from looking at those requirements and the data set how to configure their system for
um,
NEMO5.
yeah, that's correct.
I actually figured something out in this call. Is that what you're saying?
I hope I'm being more helpful than that.
No, I think that does help because it's hard to say from the outside exactly how every team operates, but
Sure.
a lot of these problems they're going to get not just in NEMO 5 but in everything else. How they configure their system, how they devote resources is there's a most efficient way to do it, and then there's a brute force that let's just throw everything at this, then it's done, let's get on to the next one.
Sure.
But
Yeah, and I think it'll be more advantageous to spend more time, seeing how the simulations perform under a, variety of kind of settings. Um,
and to have had the experience with running some different size and different complexity simulations to get a feel for, to be able to look at that data set they're going to get from you and have a feel for roughly how we should set this up.
sure.
Because this is, they're going to have four other workloads to run at the same time.
Hmm.
And so planning your work then, is that what we're saying? Plan your work, then work your plan?
I think that is a good plan.
So my old man was right about that? Okay. Getting on to the next slide, slide 10, drilling down a little bit deeper. What do they need to know?
um, 90% of the computational time when you run a NEMO5 simulation is solving linear algebra. Just 10% in sort of reading in the problem and setting it up. The rest of it is going to be in things, uh, say, dense matrix multiplies, solving eigenvalues of very large sparse systems. The packages that NEMO5 uses kind of go hand in hand, PetSea and SLEPC.
Mm-hmm.
So a lot of, in our group too is, working on ways, how can we get this one particular function, to run faster? And maybe that's by putting it on a GPU. Maybe that's by using, a particular library that's configured properly. But this is probably where the most bang for the buck is. Um,
And that brings us that you brought up an interesting point with GPUs. Let's talk about that a little bit. Student teams since 2010 have been moving increasingly towards using accelerators and trying to come up with that right um, ratio and way to use them. We see a lot of GPUs. We also will probably see some Intel PHYs as well. What is out there to support them? I'm assuming that this is that there's some CUDA code out there.
yeah, there is. And I mean, this is an active topic of research in our group as well. The For instance, if they look into the code, one thing they'll find is that we've started to use on the NVIDIA GPUs a package called Magma. And so this is basically it's the LPAC functions, but written for GPUs.
Okay.
And so we have some places in the code where we can call that. We say, hey, are we on a machine with GPUs? And if so, let's call this Magma function.
Ship that over to the
Sure,
GPUs and start cranking it there.
sure.
You have a sense for what sort of speed up they can get if this is implemented
Um,
correctly?
well, I see all different figures for what sorts of speed ups GPUs can give you. Actually, one of the things we're working on now is that how do you balance the workload between the CPUs and the GPU?
Mm-hmm.
And actually, I don't really have a good figure to say you're going to get this much speed up.
Sure.
One of the I'm actually curious to see what the teams can come up with. One of the issues we've had, and nothing against the Magma package, but one thing we've been working with is that when you offload a job to the GPU, that can only be done from one core. So we end up in a situation where you've got 16 cores or however many kind of doing the same thing. And one of them says, hey, I've got a GPU, I want to run it. Well, you've got 15 other guys that are saying, hey, I want to run mine there too. So how can you split up the problem such that you're taking advantage of the GPU and the other 16 cores too?
Now, I think that some of that has been solved with NVIDIA's Kepler GPU, but it sounds like Magma maybe hasn't been brought up to speed on all of that.
I think they're working on it.
Oh, sure, I'm sure they are. It's not trivial stuff, though.
Yeah, you're absolutely right.
In fact, with Kepler, they have essentially a virtualization ability to
I see.
where more than one core can address the same GPU,
Hmm.
and that's going to really speed up, really increase efficiency from what
Sure.
you're saying as soon as the Magma code gets there. So a smart team would go out and go ahead and fix Magma themselves.
Well,
So Jim, looking at this as students look at this, they have their system, they have their GPUs. What would they do in order to maximize efficiency?
I would probably look at what sort of, like I said, we're using the Magma package.
Mm-hmm.
We, chose that for kind of a variety of reasons, but for the cluster competition, they may be interested in choosing a different package. We liked it for its flexibility, the fact that in fact Magma can run on mics as well.
That's going to make a difference. Okay.
Right.
And by the way, for those of you on the call, Mike is the former name of the Intel Phi.
Yeah, we started, in fact, in our group, we kind of go back and forth because we've been, talking about them for so long, and I guess it's hard to teach a old dog new tricks.
Well,
So we,
you're not still calling it Larrabee or son of
no,
Larrabee, so that's good. I've actually heard people refer to them as Phis as well.
fees.
I
Okay.
know, but it's Phis. I sat next to someone on a plane who was part of the naming of it. It is Phi.
Okay, good to know.
Good to know. So probably understanding different packages. Magma is the one that is working out of the box, but they can use different packages. But I would imagine that splitting up the problem node-wise probably will have an impact as well.
Sure. Yeah, and I think that's just something that they're going to have to test
Sure.
and see how that parallelization works. So you probably look at some use some, I don't know what kind of profiling tools they may have available, but, see um, how the simulations behave, if you run it on, one node versus two nodes, etc.
Sure. And
Um,
some of that's going to be, while they're at the show, figuring it out and adding in more resource, taking out more resource.
sure.
One of the things that we'll see and that we've seen in past shows is when it comes to accelerators, the ratios are different. Some teams go at it with an awful lot of accelerators, others just have a couple.
Hmm.
And it's always interesting to see how that works out because the big thing that they're fighting in this is power. And
I see.
accelerators suck up a lot of power. If you can't keep them highly utilized, then you want to cut down the number of accelerators you have. If you feel you can keep them highly utilized, you get a big bang for your power buck. But if they
Right.
sit idle or semi-idle, it's a cost.
Yeah. Yeah. Like you say, there's a lot of things they have to weigh and see what works best for their particular configuration.
And NEMO5, like every other application out there, there isn't a uh, hard and fast rule of having this many cores to that many GPU cores, for instance.
No, there's not at this point. Like I said, we're still kind of, looking into that ourselves. Um, and we, from our standpoint, we don't have as much choice as far as how many, um, how many accelerators we have. If we run on, for instance, the Blue Waters machine, we've got one NVIDIA Kepler GPU per node.
Mm-hmm.
Whereas if we run on our new Conti machine at Purdue, we've got two PHYs per node. So, this is, brings into this whole discussion load balancing. How do you, like you said, how do you keep these things, busy?
Yeah, yeah, and that's going to be a huge consideration for the kids. In fact, in a competition they just had in Germany in June, one team brought four workstations clustered together. Each of them had four accelerators, two PHYs and two Teslas each.
Mm. Wow.
The coffee table of doom, as I call it. They had it all under a coffee table with all shuttered off, and that was a frightening hunk of machinery. The thing they found, though, is they couldn't run it all at once full speed. It blew the power
I was
requirement
lights
by a
started
lot.
dimming.
Yeah, lights were dimming all
Mhm.
over Leipzig, but it was something to behold when they did crank that thing up.
Mm.
Let's jump to slide 11, talk about MPI a bit.
I did want to mention one
Oh,
thing
yeah,
about
go ahead.
the PetSea and SLEPSea. I should say that there are kind of two approaches to looking into um, where the code can be sped up. And probably, like I said, the best way to do this would be, through some profiling to see how the code's actually behaving. We do some of these, like I mentioned, the linear algebra calls. We do, or functions that implement linear algebra routines. We do some of those directly in the code. So in the NEMO5 code, we'll say, hey, call this Magma function. On the other hand, um, we use PetSea for most of our sort of matrix storage and matrix and vector routines. And PetSea has, in their development version, they do have some GPU capability. And in fact, one of the members in our group is actually working to augment PetSea with specifically Magma capability so that PetSea can
Mm,
interface to Magma. Um, since we use PetSea for pretty much everything else, this way we can, we can call our PetSea functions like we normally would, and PetSea will know, hey, oh, they've got a GPU, so let's call the Magma version rather than us
okay.
putting that in the code. Um, so the other thing, if the students want to get into um, the actual software routines that are being called, the other thing is to look into the PetSea code and see what that's doing.
Very good. Good advice there. Let me ask you, you've mentioned profilers a couple of times. You have any recommendations there?
Uh, We use Intel's VTune. I don't know if the groups are going to have access to that.
Might be an educational license. And actually, I'm going to bet that the computer departments at pretty much all of these universities have access to some sort of profiler, if not
Yeah,
VTune, something else,
sure.
right?
Yeah, that's right. And we actually have an internal profiler to NEMO5. If people start to look at the code, they'll see these TikToks. And so we've kind of implemented these so that we can get sort of profiling results, but in an optimized, we don't have to build and debug or anything. We can,
So it has its own profiler kind of hidden within it.
yeah, and I think, I don't know if we have a lot of good documentation on that, but it's definitely there's definitely some stuff in the NEMO5 manual.
Okay.
So they can, but
That's a good hint there.
it's, if they can get their hands on, a software with a GUI, um, that's probably going to be easier to work with and see really how
Mm-hmm.
where the code is spending its time.
Good. Good hints there. Let's jump to slide 11 and talk a bit about MPI.
Sure. Um, so I imagine that the scale of, like you mentioned with these cluster systems, they're probably 2, 4, 6, 8 nodes on that
Probably
scale.
4 to 8 nodes,
Yep.
up to maybe, I don't know, what's 8 times 16? 100 cores, but
Okay.
then add in some accelerators.
Sure. Yeah, I don't really imagine communication being a
No.
big issue for any of these simulations. So Nemo 5 is built on MPI. I don't think we really do anything too fancy with it. And this is something that, but maybe students find a way to do something better. And that's something that they could, some information they could glean from a profiling
Sure.
tool.
And have a good idea of how to apportion out the system resources to what they're doing.
Right. Yeah.
So again, if you can scale to 100,000 CPUs, then you're not going to have much of a problem with 16.
Correct.
Yeah, excellent. And on our last slide here, looks like there's some places to go for further help and information and all that.
Yeah, I think I hope I covered everything here.
It's pretty good.
Let me, so the group page, I think that's the page you landed on yesterday.
Yes.
Um, this is, it's going to give you more of an overview of what the group does from a research perspective. There are not a lot of details there on NEMO 5 per se.
Mm-hmm.
Maybe its capabilities, but not so much for the, I guess, on the software aspect. But it is probably, more information there, like what we talked
Overview
about in the
kind of
first few
stuff.
slides. Yeah, these are the different types of, research problems we're working on. So I think most students, well, then to link the two bullets here, there is a link on the group page to request a academic license for NEMO 5. So NEMO 5 is free to use for academic purposes.
Mm.
So I think there's an availability link. And so if there's anybody listening that doesn't have access to the code or the NEMO 5 distribution group yet, they can fill out this very short web form. And then we distribute and support NEMO 5 on the nanohub.org, which is sort of a cyber infrastructure for scientific computing that's also run at the Network for Computational Nanotechnology. So anyway, sorry to get to the point.
A little tangent there, but that's good. That's good stuff. And it looks like
I
there's a
gotta,
lot of resources available on that Nano Hub
sure,
page.
yeah, I would be remiss in my duties if I didn't throw these hooks out for people.
Oh no, I'm glad you did. It helps.
Yeah, so on the distribution page, there's a wiki, there's a forum. People can ask questions. You can actually run simulations from NanoHub, so you don't have to compile the code at all. Uh,
Mm. Mm-hmm.
but yeah, you can get the other resources, source code. We have a static executable. It's not so stable depending on the hardware you're running on. We have that available. I'm guessing most of the groups here are going to want to build the code from source.
Yes.
Um,
Are there
the
any data sets up there they can play around with?
Yeah, so the regression tests are there.
And will running those regression tests give them a feel for how the code reacts with different size requirements and complexity?
Yeah, it should. There's a wide variety. There's about 30 tests. Some tests take 7 seconds on one core. We've built these tests to keep the code stable. It's not
Okay.
so much to
Performance
both.
profile or anything.
Yeah, well, we are interested, making sure the code, you don't want somebody to make a change to the code and find out it's 20% slower the next morning. So we are able to make sure the regression tests take, the time and memory usage is what we expect it to be. But yeah, those tests are going to be a good, basically going to present you all the cases that they might see for the actual competition.
So running through those and noting the different sizes and how they run and stuff is going to give them an idea of how they would run with a real life data set you're going to give them.
Right, exactly.
Good. That's a good hint there too.
And I think they should keep in mind, like we discussed earlier, that the two main types of simulations that we work with, which are sort of, generally speaking, the quantum dots and transistors.
Good. Good. Good.
Um, the what we do with the regression test to make sure that the answers are correct is we basically have we just like the Linux diff command, we have a slightly smarter version of that, which can basically ignore sort of numerical error. So, as especially since we're an engineering group, if we're calculating a current, if something changes by 1/100th of a percent, we're okay with that. And so the smart diff is what we use to ensure that the results are, valid from one day to the next.
Ah.
Um,
Okay.
And so I think the team should, I think, keep that in mind, that the results, the answers they get, there's some leeway there.
They're not going to be down to the final decimal place
Right.
replicable from one identical test to the other.
Right. Yeah, because there are a lot of things that are going to affect that.
Well, there's a little chaos in this whole thing. We're talking about atoms.
Sure.
Good stuff. And we've got, of course, the NEMO5 manual, which you said is complete in every single way.
It is.
Everything
It
they could
is.
possibly ever want to know is there,
We're
or a work
starting
in
the.
process.
We're printing the first and only edition is going to be hard. We're going to print hard copies, and mail them out.
Or
Yeah.
fax them.
So
You could fax them to people
fax
too.
them. um, yeah. So that is definitely work in progress. If things are not clear, we would definitely like to hear polite requests on the forum
Sure.
to say, hey, this isn't clear. But we have made a lot of progress on it recently.
Good.
And then I guess the final thing is, I don't know how much help this will be, but we used Oxygen. So this creates a nice, it's basically a web page that lets you peruse the source code.
Hmm.
Sort of see the the interactions between all the different classes, and you can look into the functions and all the member variables. I mentioned it here in case people want to look at the source but don't just want to open the source up and start scrolling through things.
I can see where that would be helpful. Most of these teams will be organized in a way that there's going to be one specialist on an application like NEMO5 and then perhaps a backup specialist. and
Sure.
this would probably help them out in their in at least getting familiar
Hmm.
with what's in there and how it's laid out and how it works for when they have to brief the rest of the team.
Sure. And this could help to, I think it could also help to see how NEMO interfaces with the libraries we use like PetSea.
Mm. Mm-hmm. Well, very good stuff. You gave out some helpful information there, Jim.
Oh, well, thanks. I hope so.
So let's hope they stick through and listen to it all, and let's have a good, clean competition.
Sounds good.
Great. And I think that we'll be seeing you in Denver, right? Maybe?
Yes, I'm gonna, I
Gonna
think
be there?
I need to register, but yes, I'm gonna be there.
Oh, excellent. And we will look forward to that. And teams, you can meet Jim in person there. You'll probably be rolling around and checking to see how you guys are doing. Thanks again, Jim. Really appreciate the time.
Oh, you're welcome. Thanks a lot, Dan.
And we'll see you in Denver.